Welcome back. So let us now consider some worked examples. Still on differentiability. This time around, examples on problems involving um, Leibniz formula. So problems for which we will have to apply Leibniz formula. So let's take them one after the other. So let's look at this problem. First, it says obtain the nth derivative. Obtain the nth derivative of x squared plus 1 e to the power of 2x with respect to x. So um, that's what we have here. Now, how do we know that we need to apply Leibniz formula, or we don't need to apply Leibniz formula? We have done problems of this kind before, where we got the nth derivative of some functions without using Leibniz formula. The interesting thing about those functions was that they did not involve two portions like this. We have this to be a product of two functions. We have this, which is a separate function, x squared plus 1, and we have this e to the power of 2x. So whenever we have a product of two functions like this, then we would want to employ Leibniz formula to simplify our analysis. So to proceed, we will still do something a bit similar to what we've done previously before we discussed Leibniz formula, which was to get the nth derivative of some function by differentiating, getting the first few derivatives and then observing the pattern, then generalizing with that pattern. So we'll do something similar here. Now, but the point is this, we should recall that by the Leibniz formula, the n of uv, where u and v are separately functions of x, was equal to the summation from r equal to 0 up to n of n combination r, the r u, the n minus r v. So that is the this is the formula. So we know that by the time we expand this out, this is going to give us when r is equal to 0, we're going to have n combination 0, the 0 u, the n v plus n combination 1, that's when r is equal to 1, the 1 u, the n minus 1 v plus when n equals 2, that will be the n combination 2, the 2u, and the n minus 2v. And that continues like that, and like that, up to getting n combination n minus 1, the n minus 1u, the 1v plus n combination n, the n u, the 0v. Okay, so now the point is this. We know this is the formula, okay, but the point here is that we have two portions of this function. We have x squared plus 1 and e to the power of 2x. So what's important is that in applying this formula, so that we can get a finite number of terms, okay, we know that the terms here are going to be dependent on the n, but we can easily simplify this if we carefully select our u and v such that the terms will soon vanish. So for instance, if we pick the term x squared plus 1, by the time we get its first derivative, it will give us 2x. Second derivative will give us 2. Third derivative will give us 0. And every other derivative going forward will be giving us 0, 0, 0, 0, 0. So we know that at every point, we have to multiply the derivative of one by derivative of the other, even though they will have different orders at those points. But we are certain that if we set u, in this case now, to be equal to x squared plus 1, we are certain that by the time we do the derivatives, okay, we start with the zeroth derivative of u, we go to the first derivative of u, we go to the third the first derivative, the second derivative, the third derivative, the fourth derivative. We know that from the third derivative forward, everything will be zero. So it will definitely clear off every other term that we have going forward. So when we carefully pick u like that, then we are certain that the terms will vanish at some point. So we don't even have to bother about all of the terms. We just have to bother about those that do not vanish. That is the first few terms that do not vanish. So that has to be carefully considered before we choose which of them should be u and which of them of these two functions now should be u and which of them should be v. Okay, so having that in mind, we say that given the function y to be x squared plus 1 into just looking at the function we're given now into e to the power of 2x, we say that let u be equal to x squared plus 1 and let b be equal to e to the power of 2x. Okay, so that means that our y is equal to u v, the product of these two. So we have carefully selected our u because we know that the derivative will soon vanish. So that by the time we get here, since the derivative starts from 0, by the time we get to where it vanishes, then we can ignore every other term that follows because we'll be having 0 multiplying some, whatever the other one is going to be. Alright, so that is our u and this is our v. So we know that for us to make use of this formula successfully, we need the first few derivatives for this. Okay, once we see that it has vanished, then we know we have to stop there. Okay, because it will give us 0 going forward. And for this, we see that when we differentiate this, it won't vanish. And for the one that doesn't vanish, we will have to get a formula for its nth derivative by the time we observe the first few terms. That is the way to apply this, okay, in all cases. So we now say that but our u is equal to, from u, so we can say that but from u being equal to x squared plus 1, it will follow that the u, that's the first derivative of u, is 2x, as derivative of x squared is 2x, derivative of 1 is 0. Then the squared u, that's the second derivative of 2x, that will be derivative of 2x, which is 2. And the third derivative, the cube u, will be derivative of this constant, which is 0. And the fourth derivative, the 4u, that will be giving us 0 as well. So we can see that as it goes on like this, we can see the pattern already that the nu will be equal to 0 for all cases where n is greater than or equal to 3. That means from the third derivative forward, we see that everything is giving us 0. So we just take note of that. Then we consider the other one, which is v. So we say that from v equal to e to the power of 2x. So we want to observe what its derivative is going to be. So let's add another an additional page here. So from this, we see that the derivative of v, the first derivative will be the derivative of e to the power of x is e to the power of x, but we have 2x here, so we have to take the derivative of this and multiply by that. So this will be 2 e to the power of 2x. Then we get the second derivative, the square v, that is 4 e to the power of 2x. Then the next derivative, that is the 3v or the cube v, that will be 8 e to the power of 2x. So we can already see a pattern here that for successive terms we just keep multiplying the coefficient by 2. Okay, so basically this already tells us that the nv, the nth derivative will be, so we can see this as 2 to the power of 1, the coefficient here is 2 to the power of 1, the coefficient here is 2 to the power of 2, this is 2 to the power of 3. So we expect that this will generally be 2 to the power of n multiplying e to the power 2x. So that is all that we need for now. So since we already have the formula for this, then we're good to go. We just go back to our expression for the Leibniz formula and just insert all of this right here. Okay, so we now say that therefore, okay, by the Leibniz formula, by the Leibniz's formula, the n of uv is equal to, of course, write out the formula again. Summation from r equals to 0 to n of n combination r, the ru, the n minus rv. So if we expand this, we know that once we get our expansion to 3, we are good to go, because from 3 down everything should be 0. So we'll just expand up to the third step. So we'll just say that the others will vanish to 0. So this is going to be equal to, for when r equals 0, this will be n combination 0, the 0u, the n minus 0, that's the nv, plus the next one, n combination 1, that's when r equals to 1, the 1u, the n minus 1v, plus the next term, n combination 2, the 2u, the n minus 2v, plus the next term, n combination 3, the 3u, the n minus 3v, plus and so on and so forth. Okay, but we know that since this one already will give us 0, okay, we can just put that right here now. What is n combination 0? So n combination 0, I mean anything combination 0 will be 1. So, okay, this is, if you like, n factorial over n minus 0 factorial multiplied by 0 factorial. So this is n factorial, cancel n factorial. So you have 1 over 0 factorial, which is 1. Then this is the 1, d to power 0, that is just u multiplying the nv, plus what is this one? That will be n factorial over n minus 1 factorial 1 factorial, and this is going to be the u, the n minus 1v, plus, so this is going to be n factorial over n minus 2 factorial 2 factorial, then we have the squared u, the n minus 2v, then plus n factorial over n minus 3 factorial 3 factorial, then we have the cube u, the n minus 3v, so and so on and so forth. Again, we are stopping here because we know the others will vanish to 0, so that's why we just don't want to bother ourselves about the rest. Okay, so going further, we know that this is giving us 1 already, so this is just u multiplied by the nv, plus this is n into n minus 1 factorial, so this is basically going to give us n divided by, if you like, you can write this as n multiplied by n minus 1 factorial, then divided by n minus 1 factorial, multiplied by 1 factorial. 1 factorial is just 1. And then we have this to be the u. So let's clean that. The u, the n minus 1v, then plus, for this also we can break this down into n minus 1 into n minus 2 factorial, then divided by n minus 2 factorial. We stopped at n minus 2 factorial because we have n minus 2 factorial in the denominator, multiplied by 2 factorial, which is 2, then multiplied by the coefficient here, which is the squared u, the n minus 2v, then plus what we have here, that's n into n minus 1 into n minus 2 into n minus 3 factorial, divided by n minus 3 factorial 3 factorial, then we have we have the cube u, the n minus 3, okay, v, plus blah blah blah. All right, so we can simplify this now. We can say that this is going to be equal to u the nv plus, so this will cancel this, so we have n over 1, which is just n, so n du the n minus 1 v, then plus, this is going to be n minus 2 factorial, cancelling this, and then we have n into, this will be n into n minus 1 divided by 2, then the squared u the n minus 2 v, then we have this to be plus, this is going to cancel this, so what we have left will be this, and this is 3 factorial, which is 6. Okay, so basically we're going to have this to be n into n minus 1 into n minus 2 divided by 6, then the cube u, then the n minus 3 v plus, and so on and so forth. So that is how this works. And now we have all the we have expanded this already, and then we have all the terms that we need right here. We already know what the nv is, so the nth derivative of v is 2 to the power of n e to the power of 2x. Okay, and then we know the derivatives that we require also from u. Okay, so we just put them right in here. So this is going to be equal to, don't forget our u is x squared plus 1. Yeah, x squared plus 1. Just checking the question again. That's x squared plus 1. Then the nv, we know it is 2 to the power of n e to the power of 2x. Okay, then plus n multiplied by du. Du is the derivative of this. We found that already up there. That was 2x. Then the n minus 1b. We just replace n in this situation with n minus 1. Okay. So the difference between the n and the n minus 1 is that we are replacing n by n minus 1. So this will be 2 to the power of n minus 1, then multiply by e to the power of 2x. Okay, that's what we get for this situation. Then the next thing is n into n minus 1 divided by 2. Then we have the square u, that's the derivative of this, that is multiplying 2, then multiply by the n minus 2 of v. The n minus 2 of v, that will be 2 raised to the power n minus 2 multiplied by e to the power of 2x. Okay, the same thing, just replacing this n minus 1 now by n minus 2, or say we're replacing n here by n minus 2. So that's that for this case, and then plus the next one. This is n into n minus 1 into n minus 2 divided by 6, then multiply by the cube u. The cube u, that's derivative of 2, which is 0. Then we have this to be 2 to the power of n minus 3 e to the power of 2x, and then plus blah 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 plus, we know all of this will just be 0. Okay, so just like this is 0, every other thing will be 0, because this will keep being 0 and it will keep cancelling them off. So basically these are the only terms we have left. So that was why we had to choose our u and v that way. Okay, so that we easily get to the point where the terms cancel out. So we add a new page here just to move forward. Okay, so this is going to be equal to, we can just simplify what we have here now. We can see that 2 to the power of n e to the power of 2x is common to all of them. So we can move that out. So when we move that out, we bear in mind what we're going to have left. 2 to the power of n and e to the power of 2x. Okay, so we know what we have left here is 2 to the power of n minus 2. So let's move 2 to the power of n minus 2 out. So this is 2 to the power of n minus 2 e to the power of 2x. Okay, and then let's see how that affects every other thing we have here. We moved out 2 to the power of n minus 2. So it should be that by the time we bring that back in, it will give us this expression here. Okay, so that means what we have left here will be um let's see how this works now. If we have here 2 to the power of n, so if we moved out 2 to the power of n, to give us this expression. Now we have 2 to the power of n minus 2. That means we should have inside 2 to the power of 2, because if we have 2 to the power of 2 inside, by the time we multiply it with this, when expanding, it will give us the same result as this. So this is just going to be 2 to the power of 2, okay, for the coefficients of this that we have left. So we're going to have 2 to the power of 2, which is 4 into x squared plus 1. Okay, so that's what we have left from this term. Then plus, so for this we have 2 raised to the power n minus 1. So that means we should have 2 to the power of 1 right inside. So that by the time we multiply it by this one outside, it will give us 2 to the power of n minus 1 that we have here. So basically we have 2 outside. So 2 multiplying this, that will give us 4. So basically we're going to have this to be 4x multiplying n. So that's what we have left from this. And then we go to the next term. We have 2 to the power of n minus 2 already moved outside. So everything here remains as it is. So this will be cancelling this. And then we have plus n into n minus 1. And then we close the bracket. So basically that is all that we have left. And indeed, this will give us the nth derivative of the given function. So that is how we apply the Leibniz formula. Is quite easy to deal with. We carefully select our u such that its derivative vanishes. That is, we identify the portion that its derivative vanishes quickly, and then we pick that as our u. Then the part that its derivative does not vanish, if any, we will pick it as our v. Then write out a general expression for its n derivative so that we can easily substitute it in the formula, in the Leibniz formula when applying it. So this is how it works. Then whatever is left at the end of the day will simplify as we have it here. So that is that about that. Let us consider quickly. Let us consider another problem where we still have to apply the Leibniz formula. So this will be problem 2. Well, to obtain the nth derivative, still want to obtain the nth derivative of another function, which is a product of two functions. Obtain the nth derivative of y equals x cube. So we have this to be y equals to x cube cos x. Okay, and we want to get the derivative of this with respect to x as before. All right, so let's see how this works. Again, we can now carefully pick what should be our u in this case. U is meant to be that portion that its derivative will soon vanish. We know that cannot be cos x, because derivative of cos x will keep giving us, taking us to minus sin x cos x, sin minus cos x, and back and forth and back and forth, like we examined when we began this chapter. We saw that the derivative of cos x could actually be generalized in terms of cos x, okay, which we did together in a previous lesson. So you can get back to that and examine how we came about that there, because we're going to make use of that result here. And so the part that the derivative will quickly vanish is x cube. So we can simply say that let u be equal to x cube and let b be equal to cos x. So if that is the case, then we can just do the derivatives together. The u will be equal to, that's the first derivative of this, that's 3x squared, and the b will be equal to the first derivative of this, which is minus sine x, okay, which we have seen before that this is the same thing as cos x plus pi over 2, that is cos of x plus 90, okay, will give us this result. And we say that when you get the second derivative of this, the square u, that will be 6x, and the square v, the second derivative of this, will be derivative of sine x is cos x, so this is going to be minus cos x. And we said that this was the same thing as cos of x plus pi. This is pi over 2 multiplying 2, multiplied by 2, that's 2 of pi over 2, which is pi. That's cos 180 plus pi. So we know that that is on the third quadrant, so, and cos is negative on the third quadrant as expected. So this is equal to this. And we can come here. the cube u is going to be equal to the derivative of this, which is 6, and this is going to be the cube v, and that will be derivative of minus cos x. You know, derivative of cos x is sin x, derivative of cos x is minus sin x, derivative of minus cos x will be sin x. Okay, and we are able to see that that is the same thing as cos of x plus 3 multiplied by pi over 2. Okay, and so on and so forth. But let's move further. We know that the 4u, that's the fourth derivative of this, will be 0, and the fourth derivative of this, if you like, will be derivative of sine x, which is cos x. And basically, this is the same thing as cos x plus 4 pi over 2. So 4 into pi over 2. We know that 4 times pi over 2 is 2 pi. So it's just like we're adding x and 2 pi. So that does not change, it doesn't change the value. So it remains the same as what we had before. This is just to see a general pattern so that we can generalize. We've done this before, we've explained, we've seen together how all of this came about. So we're just using that observation right here directly. So we can see already that going forward from here, our derivatives will keep being 0. So we observe that the nu will be equal to 0 for all n greater than or equal to 4. Okay, so we end that there. And for this, we are able to generalize also that the nth derivative, the nv, will be equal to cos x plus n multiplied by pi over 2. All right, so that is that. That's what we need. So it's just good that we do them together this way. Okay, it saves time and space. All right, so the next thing is we now recall that that means if u is equal to this and v is equal to this, as we have stated here, that means our y, is equal to uv, and then our dny, so now see that does by the Leibniz formula, derivative of this with respect to and the nth derivative of this, the ny, that's the same thing as the n of uv, will be equal to the summation from r equal to 0 to n of n combination r, the r u d n minus rv. All right, so we can now expand this out. We know that it is from the fourth term that it becomes 0, so we should expand as far as the fourth term, then we can leave the rest because they will vanish to 0. So going ahead with that, let's add the page here. So going ahead with the expansion, we know that when r equals 0, this will be n combination 0, and we're going to have the 0 u, the n minus 0, that is n b, plus n combination 1, the 1 u, the n minus 1 v, plus n combination 2, the 2 u, the n minus 2 v, plus n combination 3, the 3 u, the n minus 3 v, plus n combination 4, the 4 u, the n minus 4 v, plus and so on and so forth. It continues like that up to the last term. We've just stopped here because we know that this will just vanish. Okay, this will become 0 from here because we know that the 4u is 0. The 4u and every other thing forward for u is going to be 0. So that will keep ensuring that every other thing here will vanish. Okay, so this is the only thing we have to deal with. From previous work, we already know this is 1. Okay, we can just write it out. 1 multiplied by, this is u, multiplied by the nv. Okay, and then we know also that this is n. So this is just going to be n multiplied by the u multiplied by the n minus 1 b. Then we know that n combination 2 is n into n minus 1 divided by 2, okay, from 2 factorial. and this is the squared u the n minus 2v. All right, then plus the next one. I can remember what we did up there. That's what I'm just writing out. So that this will be n into n minus 1 into n minus 2, then divided by 6. Okay. So you can easily expand that again. If you can't remember that, you can easily do this expansion again. You see that it's going to give us this result. All right. So there's no need to do the expansion again since you already know what it is. Okay. So this is going to be the 3u the n minus 3v, then plus this is going to give us something like n into n minus 1 into n minus 2 into n minus 3, and then we're going to have this to be divided by 4 factorial. So this was 3 factorial here, this was 2 factorial, this was divided by 1 factorial, which is 1, 0 factorial, which is 1. Okay, so this will be divided by 4 factorial if you expand it out. So 4 factorial is 4 times 6, which is 24. Then this will be the 4 u the n minus 4v, and then plus and so on and so forth. So we know already what to insert now. U, according to the question and what we've identified up there, u is x cubed, v is equal to x, so we know what to do right here now. So this is just going to be equal to x cubed multiplied by the nv. We have seen that the nv is cos x plus n pi over 2. So just put that right there. Then plus n into du. Du is the derivative of this, which we've obtained up there to be 3x squared. And the n minus 1v. Just change this to n minus 1. That will be cos. Let me write that out. That will be cos of x plus n minus 1 multiplied by pi over 2. Okay. Then we go to the next term, that is plus n into n minus 1 divided by 2 multiplied by the second derivative of that's the derivative of this. We obtained it earlier to be 6x, then multiply by the n minus 1, n minus, where's that? N minus 2 derivative of this v. So that will be, we just replace n here by n minus 2. So that will just be cos of, so let's put this off. This is cos of x plus n minus 2 multiplied by pi over 2. So close the bracket. Then what do we have left? I mean, we've gotten up to this. Then the third one is plus n into n minus 1 into n minus 2 divided by 6. Then the 3, that's the cube u, as the derivative of 6x, so that is 6. So this will be multiplying 6, then multiply by the n minus 3v. That will be cos of, if we just replace n by n minus 3 in that expression, cos of x plus n minus 3 multiplied by pi over 2. So we close the bracket. Okay, that's all for the fourth term. Now we move to the next one. We know it will be 0, but let's write it out anyway. So this is going to be n into n minus 1 into n minus 2 into n minus 3 divided by 24 multiplied by the fourth derivative, that's the derivative of 6, which is 0, then multiply by the n minus fourth derivative of this. This will be cos of x plus n minus 4 multiplied by pi over 2, and then close the bracket. So with this, we are good to go. We know that the rest will also vanish to 0, so that just will just be 0, just as this will be 0. So we just wrote this out so that we can easily see how everything vanishes to 0 from this point forward. All right. So the terms we have left are now obvious. We can now simplify them. So looking at all of this, it appears that nothing is common, so we can just leave it as it is and just write this out. This is going to be x cubed multiplied by cos of x plus n pi over 2. Then this will be plus 3nx squared cos of x plus n minus 1 multiplied by pi over 2. then plus the next one is we're dividing this by 2, so this will be 3x. Okay, so this will be 3x into n multiplied by n minus 1. Then I mean that's the coefficients we have here. Then multiplied by cos, this will be multiplied by cos of x plus n minus 2 into pi over 2, then close the brackets. Then the next term here, this is 6, so this 6 will cancel this 6. Then what we have left will just be plus n into n minus 1 into n minus 2 multiplied by cos of x plus n minus 3 over n minus 3 multiplied by pi over 2. So this is n minus 3 multiplied by pi over 2. And then we close the bracket. And that is all. Every other thing will vanish to 0. So is there anything to extract here? Anything that is common that we can extract? There is no need. So we already have our formula. This is the expression that we need for the nth derivative of x cubed cos x. So life is as easy as that. Again, in summary, to apply the Leibniz formula to get the nth derivative of a function, that's the product of two functions, of course, we identify what portion to be our u. We usually pick that to be the portion that its derivative will vanish to 0 after some time. And then the portion we pick as our v is the one that the derivative does not necessarily vanish to 0, but we can get a formula for the nth derivative. And so that is that about that. We'll proceed from here in the next lesson to consider other examples. Thank you for watching.